Okay, so now let's take a look at part C of this same problem. So now we're still working with the pendulum, and we have the system of equations given over here. This is a non-linear system. And so we took a look at the case where we had equilibrium set up near theta is equal to 0. We have other equilibriums. So for example, if we have the conditions that theta v is equal to pi 0, we show that that's an equilibrium as well. So if we set it up at position pi, that means at time 0, it's located straight up at its vertical position. And we haven't had any velocity. So if you were able to balance a pendulum perfectly like that, it's not going to move. So that's why this is an equilibrium. But if you want to think about whether this equilibrium is stable or not, then you can think about, well, if I had a solution which an initial condition which is pretty close to that, say like over here, where theta is not quite pi. So maybe theta is like 5 pi over 6, and we still don't give it any velocity. And that's pretty close to what the equilibrium is. And then if you hit play, in other words, you let go of that pendulum, what's going to happen? Is it going to swing this way, or is it going to swing this way? Well, because of gravity, it's going to swing down, and it's going to wind up settling back down over here at the other equilibrium. So this is a unstable equilibrium we would expect for this example over here. So we can prove this with some intuition, but we don't have the mathematics yet to be able to show that that is not an equilibrium, or not a stable equilibrium, excuse me. It is an equilibrium, it's just an unstable equilibrium. And so one nice tool to play around with is if you go to this link over here, there's a GeoGebra app, and I've linked this in Canvas. So let me jump over there. It's going to take me a second on Zoom. And that's what we're looking at over here. So here's this app. And you can see that we have, looking down at the lower left corner of this window, we're working with the same exact equations that we have. They're calling theta x, and they're calling v y. Otherwise, it's the same equation. So on the top, we have d theta dt is v. On the bottom, we have dv dt is equal to minus 0.2 v minus the sine of theta. Okay, so we just needed to change those letters. So what we're looking at here is we're setting up the pendulum at its, now we're thinking about what happens when we change the velocity. So I'm going to set up a pendulum. It's hanging at its equilibrium position. And instead of moving it and then letting it go, I'm going to leave it at its downward hanging position and then push it. So if I give it some push, right, what these solutions are saying way back on the first slide, we said if we give it a little bit of velocity, then what you expect is the pendulum's going to go back and forth and back and forth. And then due to air resistance, eventually it's going to settle back down at its downward position, but it never does a full loop all the way around. So on this horizontal axis, we're looking at values of theta, and on the vertical axis, we're looking at values of v. And so over here, someplace between 2 and 4 is 3. That's approximately pi. So you can see with this setup, the pendulum is rotating back and forth, but its position never reaches as large as pi. So it never flips all the way up to its upward vertical position. But if I give it enough velocity, eventually it does. So a solution like this, what we can see is this pendulum now has passed over pi. So it's done one full rotation, and then that's it. And then it settles back down at its position, theta equaling 2 pi. So that means it has done one full rotation. And we can keep giving it more and more velocity, and you can see at some point, you can push it so hard that now it goes all the way around once, it goes all the way around twice, and then settles back down at its equilibrium at 4 pi. So as we suspected, all of these equilibrium at pi, excuse me, at 0, at 2 pi, at 4 pi. These are all stable equilibrium. The pendulum wants to wind up settling back down at its downward vertical position, whereas the equilibrium, when theta is equal to pi or 3 pi or 5 pi for odd multiples of pi, this is going to be when the pendulum is initially set up at its upward vertical position, and that's really unstable equilibrium. And so on the previous slide, it asked us to identify what initial velocities would be enough to make it go all the way around, but just once. And so playing around with this, we can see if we gave it an initial velocity of 2.4, that's not going to be enough. Here, we haven't gone all the way around. But if I give it just a little bit more initial velocity, now that is enough to send it all the way around. So one thing that we can observe is that the velocity needs to be bigger than 2.4. Because when we had it at 2.4, it didn't go all the way around. When we make it bigger than 2.4, now we've given it enough velocity that it's going to flip all the way around. But if we give it too much velocity, it's going to go around more than just one time. And we can see that happens right there. So as long as the initial velocity was bigger than 2.4 and less than 3.6, those are going to be the situations where if we start the pendulum at its downward position and give it those velocities, it's going to go around once and then eventually settle back down at its equilibrium position when theta is equal to 2 pi. So here, this is just some intuition that we can play around with the pendulum in order to eventually match the mathematical analysis that we can show with our techniques we're going to develop for nonlinear systems.